Hello everybody, welcome back. Justin Miller, Oxnard College Physics here, looking at some more magnetic fields, and just want to get started with this. So, we looked at the magnetic field due to a current segment. That was good. We extended that out into a infinitely long straight line and found the magnetic field for that. That was good too. What about if we said, what does the magnetic field say at the center of a circular current loop? So we can go ahead and take ourselves some sort of circle here. Let's just say that this has some radius r. We have some current in here. I will just say that it is rotating, not rotating, but cycling around in a clockwise manner. And we want to know, what's the magnetic field at the center? So first off, let's get an idea of the direction of the magnetic field at the center here. So we've got all these little current elements, which we could break up into being along the path, ds, which goes all the way around, yes? But we look at all the individual contributions here, right? So we can go ahead and put your fingers in the direction of the current element, and point your palm into the vicinity in space where you're trying to determine the direction of the magnetic field. I crossed into R, and your thumb will be left in the direction of the magnetic field. So for this little element right here, we have currents going that way. I'm looking into the middle here. Magnetic field would be into the board then. So that's good. What happens if we look at another one, say, over here? Well, we've got that element there, it's going that way. We again still want to look in the center here, point our palm that way, thumb still into the board. So this current element and this current element ultimately both produce magnetic fields that are directed into the board, really anywhere in the interior of this loop. We're really going to only be interested right now in the center here. But at any rate, you can see that no matter where I put my hand in terms of the direction that the current's going, if I'm always pointing my palm facing into the center of the circle, whoosh, what do we have? The direction of my thumb is always into the board. So what do we get from that? Well, we get that the contribution overall for every current element within the circle produces an inward directed magnetic field. So I can already say the direction. For this current being in a clockwise manner. We reverse the direction of the current, we change the direction of the magnetic field. That's what we get inside the loop. So we've got the direction gotten, that's good. What about actual magnitude? Well, to get that, we got to go back to the Biot-Savart Law. So we've got that the magnitude of the magnetic field itself will be equal to the absolute value of the integral of mu 0 I over 4 pi r times ds hat across r hat. There we go. So we want to utilize this. Well, we know that mu 0 I and 4 pi are all constants. Those can come out. And we've already gotten really this cross product relationship in terms of the direction. So we know that ds and r are perpendicular to one another. If we're looking exactly at the center here, r hat's always going to be radially inward. perpendicular to ds hat, because it's a circle. So this ds hat cross r hat in this particular case, r hat is just equal to ds. And we do have a direction, that is true. The direction is perpendicular to both ds and r, which is, we're just going to put inward in this case. So, with this, we already know the direction, and this resolved down into just a plain old ds. So let us expand it out on that a little bit. Rewrite the magnitude of the magnetic field at the center being equal to the integral of mu 0 pi over 4 pi r squared, r squared ds, absolute value. All right, so what do we do with this? Well, integrate over that circle. That's it. Let's go ahead and see what's constant, what's not. R. Well, R is the distance from the current element in question to the point in space. R is equal to the radius of the circle since we're just looking at the center here. R is equal to capital R, which is a constant here. Again, because we're only looking at the center of the circle. So this whole thing right here is just one constant. So this just becomes the integral. Let's not put integral yet. Let's pull all this stuff out. Mu 0 I over 4 pi r squared is the integral of ds. There's a couple things that we could do with this. We could just say, well, what is ds? And say, oh, that's the circumference of a circle. Or we could rewrite this in terms of what ds is with respect to some sort of polarization or polar coordinates. So let's just write this like this. Note that ds is equal to r d theta by association of arc length and angle. And we can write this as mu 0 I over 4 pi r squared times integral of r d theta. And what are we doing with theta? We're going to go from 0 to 2 pi radians. So we go all the way around the circle. What does that give us? It gives us 2 pi times r when we evaluate this whole thing, which is the circumference of the circle, right? So whether we said ds was 2 pi r or we integrated r d theta, we're going to end up getting the same thing. And we get that the magnitude of B is going to be equal to mu 0 I 4 pi r squared times r times 2 pi, which is then equal to magnitude of B hat. Factor of r goes away, factor of 2 goes away, and the pi goes away, which leaves us with a mu 0 I over 2 r. There is the magnitude of the magnetic field at the center of a circular current loop with current I. And the loop has a radius r. Nice and simple. So that's one thing. What else can we do? Well, I'm going to do too much more in terms of determining magnetic fields, but there's some other ways of determining magnetic fields other than just using the Biot-Savart Law. There's also what is known as Amperes Law, which is sort of like a Gauss's law, but for magnetism. Ampere's law used to determine B hat for highly symmetric cases. So just like Gauss's law was really only useful for cases where you can argue lots of symmetry and make lots of correlations with directions, Ampere's law is sort of the same thing. But ultimately, Ampere's law says the integral over a closed loop, in this case, a surface integral, is of b hat dot ds hat is proportional to the current that it encloses. And the constant of proportionality is the permeability of free space. So the integral of bds over a closed loop, called an Amperian loop, is proportional to the current that it encloses. So we can take something like a long straight wire with current I, and we can draw a little Amperian loop around this where it's centered upon it, and it's really more in the perpendicular to the plane of the board. So imagine a loop that's like this, now kind of concentric about this line here. And we should note that we can argue things like, as long as we're the same radial distance away from this wire, the magnitude of the magnetic field should be a constant, and that the direction of the magnetic field itself is going to be, well, it's going to be parallel to the segment ds hat. So we know already the behavior of the magnetic fields in terms of the directions. It's like they form these concentric circles directionally around the current in general, and this can be reduced down into this b dot ds goes away, and we're left with b being just a magnitude. We've got this Q0I, and then what do? What is the integral of ds? Well, we can say that this loop here has some radius r, and it's a circular loop. So ds is just equal to 2 pi r. So we've got b times 2 pi times r is equal to mu0 times I, giving us the magnitude of the magnetic field is mu0 I over 2 pi r, which is what we got for an infinitely long straight wire. The distance r away from it, the wire has current I in it, and that was the magnitude of the magnetic field. So it's just something else. We're not going to really use a whole bunch in this class. It's something that you may see at higher levels more in terms of determining magnetic fields due to specific types of cases. But this is just worth showing. Lastly, we can look at what's known as a solenoid. It's basically like just an electromagnet. Coil, N turns, and current I. Through the coil. Solenoids. Acts as an electromagnet. So we basically have this coil like this, and we go ahead and connect it to some source potential. And what do we get? We get there's a current going through here. There's some current I cycling through all these little loops here, And assuming that these loops are packed really closely together and that the cross-sectional area of the area enclosed by the loop itself, not the cross-sectional area, but the area enclosed by a loop is dimensionally much, much smaller than the length L of this, then it can be shown, I'm not going to bother to show it here, it can be shown that the magnetic field inside the solenoid is approximately uniform. It has a magnitude equal to mu 0 Ni over L, whereas N turns. L is the length, N is the number of turns, I is the current, substantiated by, you put in a little resistor here. I'm not going to really worry about that. But what do we get? We get that the current in here, going around like this, would produce a magnetic field within this that is uniform in direction and has a constant magnitude inside the solenoid. For an ideal solenoid where everything is packed together, the magnetic field on the outside drops basically to 0, but there's certain dimensionality restrictions regarding that. You're going to see solenoids referenced in your book. Ultimately, again, they're just our electromagnets. Give a little demo here in a second with that. And there's the magnitude of the magnetic field due to it. So let me grab something, we'll do a little demo. All right, so what I got here, it's got a battery here, got a couple other little things. I got some needles here, I got a magnet. So this is a nice permanent magnet. How do we know? Let's check out. Oh, look it. Picks up all these needles because the needles have some steel in them, highly magnetizable, and there we go. Oh, dropped a couple. Get them back up, put them in here. All right. So we know this picks up some needles, and then I've got this. This is a piece of steel wrapped with some wire here, some copper wire that, that's it. It's a piece of steel wrapped with some copper wire. What's going to happen when I bring it next to these? That's right, nothing. Nothing's going to happen because this isn't a magnet. This is just a piece of steel. This is a magnet. The magnet picks it up. The steel doesn't. Oh, all of a sudden something happened here. Well, that's because steel's magnetizable. I brought it by the magnet, and that acts like a magnet too. So let me get these off of it again. Make sure I'm not tricking you. Not deceiving anybody here. And bring it back by itself. It doesn't do anything. Whereas I bring the magnet, it does. All right. So no tricks. No magic. Now, I want to take this wire loop here and plug it into the battery. Connect it. I'm going to connect one side positive, one side negative. Ooh, some sparkies. Good, now there's some current flowing around here. I can feel it heating up. Ooh, due to that current. That's good. Now what happens? Well, this wire here is basically a solenoid. We got that it's producing a magnetic field. And the steel that's wrapped around can house magnetic fields. It's highly magnetizable, so it becomes like a magnet now. Let's see if that's the truth or not. Oh shoot, doing the same thing that the magnet did. Let me just connect this, see what happens. Oh shoot, now it's not like a magnet anymore. Now notice that it's still holding on to some of them, but the magnetic field that it was producing, or that it was carrying, is greatly diminished. And ultimately this starts dropping off and well, sometimes it'll house a residual field a little bit, but what one can do is sort of knock around the magnetic domains, and then kind of everything goes back to neutral, randomized orientations of the magnetic domains. Until once again, plug it on in, DC, and sparkies. Again, we got ourselves a magnet. Oh, disconnect. No magnet. Reconnect. Yes, magnet. And that's it. So that's kind of the workings of electromagnets. They're basically just current loops. So if you ever need a magnet, but all you got is some wire and a battery, guess what? You can make your own magnet. So be careful. All right, that's it. Thanks, everybody.